Hello students, today I would like to review with you the second part of topic 3, a little rundown on the last part of topic 3 on regular languages. So we've seen in the previous little video that the DFAs, deterministic finite automatas, are all also part of the NFAs, non-deterministic finite automatas, and NFA is a generalization over DFA. But we also saw that the two are equivalent if we consider the languages that they recognize. Okay, so we've seen, we've actually proved, we saw very quickly, we went through the proof that for each automata that is non-deterministic in this space of the Venn diagram, there is an equivalent one that is deterministic. So they both recognize the same class of languages, and the class of languages they recognize is called regular languages. And regular languages include all languages that can be described also as a regular expression, right? So you're going to have, A star, sigma star, sigma being the alphabet, any combination, A union B star. All of these are regular languages. So actually, regular expression is a very convenient way of describing a regular language or generating a regular language. So we can also say that the NFA and DFA in this respect are equivalent to regular expression because regular expressions generate regular languages. Okay, so there's a little bit of terminology here. We say that an automaton recognize a language and a regular expression generate a language, but they are equivalent because they both generate the same class of languages. They both generate / recognize the same class of languages. Okay, so that's what we saw last time. Now this part of the topic 3 is really interesting because we're reaching the notion of limit. And as we saw in the introduction, limit in this course is crucial. We are basically studying the limits of computations. And there are many limits because there are many different levels of computation. There are different levels of computational power, of expressivity, of languages. Here we have been studying in chapter 1 of the book and topic 3 of this class. We've been studying the class of regular languages corresponding to these automata and regular expressions, and we've seen a lot of properties of these languages. Now we're reaching the limit, right? We're kind of studying this border, this limit. And we're interested in what is inside and what is outside, right? Are there languages outside of this limit, right? Are there languages that are not regular languages? And of course, the answer is yes. And when we start studying that, we find all kind of really interesting results that lead to a whole other world of investigation in computing theory. So that's why the study of limits are very important, because they give us a lot of very interesting results, both about what is within the limits and what is outside. And so it's a whole other field that is open to us once we start realizing, oh, there are some languages that are not regular, and what are they? Okay, so let's take an example. Just to see how tricky it is actually to recognize what is a regular language and how quickly we can get to something that is not a regular language. If I give you 0, 1, the language 0, 1, okay? So if we want it to be Okay, it's just 0, 1. Okay, that's clearly a regular language, and actually I can very easily build an automaton that accepts this language. What about 0, 5, 1, 5? By this I mean 5 zeros and 5 1. One next to each other. Okay, that's also very easy, right? It's basically you have 10 states in your automaton. You do 0 5 times and then 1 5 times. Okay. What about 0 star, 1 star? So this is regular. Okay. This is regular. What about 0 star, 1 star? We've seen this one actually many times. That's a regular expression. So by definition, because it's a regular expression, right? It fits the criteria of what a regular expression is. It is regular. And here, same thing, we can build an automaton that is such that it will accept any number of zeros and then any number of 1. Okay, that's not too complicated. What about 0n, 1n? So here, the set of W such that W is 0n, 1n when n greater or equal to 1. Okay. Or to 0, doesn't matter. That is not regular. And the reason is that you can try to build this automaton. You're gonna at some point reach the difficulty because you need to be able to recognize, okay, 0, 1. You need to be able to recognize this one and this one, which would be actually not a problem, right? If our language contained both of these, you could have just a separation into two different, you have 2 epsilon, one that recognizes 0, 1, and then recognize the 10 states. But here we want to recognize this one, and all others that have exponents here such that they are the same, right? So the same number of zeros and the same number of 1 after that. That seems like something that should be computable, right? I mean, that seems like something that a computer should be able to recognize. And a reason for that is that you encounter it in any kind of IDE or syntactic parser for code when the IDE is checking that you have the right number of brackets, for instance, right? So a very similar language to that is the language set of W such that W is equal to bracket, opening bracket n, closing bracket n, right? With n greater or equal to 0. That's a way to check that it's basically the language of well-balanced brackets, right? You have as many opening brackets as you have closing brackets afterwards. And here it's not too subtle because you cannot have like weirdly nested brackets. It's just like a bunch of opening brackets and a bunch of closing brackets. But you want to define this language that doesn't seem too complicated. Well, but it's still, because this one is not regular, this one is not regular also. And the basic intuition of why it's not regular and why you cannot build a finite automaton that will recognize this language is because you need to keep track of how many opening brackets you have when you start closing the brackets. You need to keep track of how many zeros you have when you start taking the inputs, the 1 as input. And to keep track of that number, you need some kind of memory that a finite automaton doesn't have. You need some kind of memory or stack that will remember how many inputs you have accepted so far until now. And we don't have this memory. We don't have that. In some sense, you could say you would need a kind of writing capability, while the NFA and DFA only have a reading capability, right? You could say that this is a read-only, and for that you need read and write. Okay, so that's another level, and that's why this is outside. Okay, so for instance, 0 and 1n is outside. It is outside of the regular languages. How do you prove that? It's very hard, right? We can think of it and try to build an automaton that will recognize 0 and 1, and then we'll quickly realize that we can't, or that it's too hard. We're not successful. But that's not rigorous enough to prove that it is not a regular language. How would you prove it, right? Technically, to prove it, given what we've said about regular languages, you would need to prove that there is absolutely no finite automaton that recognizes this language. But as you know, to prove the non-existence of something is in general very hard, right? You usually don't do that. You prefer to find the existence of something rather than the non-existence of something, right? And for that, we're going to have to use a lemma called the pumping lemma. That is quite important. That tells us a characteristic. Okay, so the pumping lemma is a lemma that gives us certain features of characteristic that are systematically true of any regular language. And we use this characteristic and this pumping lemma to prove that a language is not regular. So here is how the pumping lemma works. And I'm going to try to present it to you and explain it to you on the same page. The pumping lemma. Okay, so to present it to you, you have a formal like definition and proof in your book, but I'm going to try to give you a sense of how it works and why this lemma holds. So this lemma is stating three characteristics. But before we look at these three characteristics of regular languages, let's take. I found this. This belongs to my young daughter, and I thought, oh, that can actually be a useful little toy or artifact to present the pumping lemma. So I'm gonna just put the paper in the middle. It's gonna be easier. So okay, imagine that this is a string that is accepted by a finite automaton. Okay, by a finite DFA or NFA, it doesn't matter. The string is accepted as an input. It's recognized, okay, by the automaton. Each of these actually don't represent the symbols on the string. It represents the succession of states it is going through. So say, you could say, this is like Q1, Q15, Q35, Q10, Q7, etc. Right? So this is the succession, and you start with Q1. This is a succession of states, of machine states it's going through. Okay, we define our machine because it's a finite automaton. It has a finite number of states, right? So the number of states we say is P. Okay, and P is actually going to correspond to our pumping number. It's called the pumping number, but we just define it as P. Okay, P is a number of states. Now, the pumping lemma says take a string that has inputs. So these are the inputs of the string, but they also represent. They actually represent the succession of states it's going through, right? So we don't care too much about what actually the input 0, 1, A, B, C, but we really care just about these, and let's say that they all represent like different states. Okay, we could even say that maybe the colors, but I'm not too interested in that because the colors are way too much the same. So I prefer to imagine that these are all like different states. They don't have to be, but different states in the automaton. Okay, so these are the different states to go through, and we have a condition on our string, right? The length of the string S has to be greater than P. And the reason for that is that we want the length of the string to be greater than P, because if it's greater than P, then necessarily it has to go to the same state twice. At least one state is present twice, right? Why? Because if your string is greater than the total number of states in the machine, then there is no way to go through all the string without at least repeating twice, but maybe more than that, the same state. So what does it mean? It means that somewhere here we have a loop. Somewhere here we're going twice through the same state, at least, right? That's a minimum. But that's the minimum condition that we need, and that's all we need. We just need 2. And so we show that if it's the case, then we have a loop in the succession of states here necessarily. So let's assume that actually this is Q13, and this other big white ball here, I should not write on that. This other big white ball is also Q13, right? And whatever it does before or after doesn't really matter, okay? But we're just saying, well, actually, all of these are different, but the big white here are actually the same. It's Q13. And these are the first 2 that are the same. All of the others are different. And what happened after, it doesn't matter. It can go on for a long time. It doesn't really matter. So if they are the same, then that means that really what's going on is that we are looping here, right? We're looping here, and we have something like that, right? We have a first piece of different states. Then we have one special state, Q13. Then we have a loop, and we go back to Q13, right? Because we assume that these are all different, and Q13 is the very first loop in the string. And then something goes on forever, and we don't know what happens next. It doesn't really matter. Forever. It doesn't go on forever, sorry. It goes on for a certain time, but it doesn't matter what happens next. So what the pumping lemma says is, well, just separate your S into 3 pieces, right? We can say that S equals X, Y, Z. This is X. Okay. This is Y. And this is Z. Okay, sorry, it's kind of hard to. Okay, so you have X, Y, and Z. And because of the fact that we took the very first that is repeating itself, then we can deduce several things. First, we know that the size of Y has to be greater than 0. Because even if you just had the white ball, you would still have a loop of size 1, right? So it's at least 1, and it can be more than 1, but it's at least 1. Second, and we know that this loop exists again, right? Or we know that it exists because of this assumption. Very important assumption. We took a S that is greater than P. If there is no string that is greater than P in our language, that's fine. Okay, the lemma still holds because it's true only for S greater than P, right? But for many automaton, you're going to have, this one, for instance, doesn't have any S greater than P. But for many automaton with regular languages like that with stars, you're going to have one necessarily. Okay, so we know that Y has to be greater than 0. That's the first result of the lemma. We also know that XY as a whole, the length of XY is less than P. Well, why is X combined with Y less than P? Well, remember we said that these are all different and these are all different, right? And the Y, now we made a loop on it. So we kind of have only, the 2 balls are put into 1, okay? So we only have here different states. If they are all different, then the sum of all of these cannot be greater than P, because P is the number of states, the total number of states, right? It's the total number of states in the automaton. So XY, the length of XY has to be less than the total number of states, because XY is composed only of completely different states. And the third result that is very, very important, and the one we're going to use to show that a language is not regular, is that X, Y, I, Z also belongs to the language. Okay, assuming that the machine M, S is in the language that that is recognized by the machine M. That we're talking about. This is and so that's the important result. What does it say? Well, it says, well, if you go through exactly the same first piece X, and then you loop with Y multiple times, you stay in the area of the strings that are accepted by this automaton. You stay in the same language, and then you can do as many times as you want, and then you have to finish with Z. Okay, so X, Y combine as many times as you want, and then Z will also belong to the language. That's a necessary result of this lemma. Okay, and this one is very important, and this is the one we use to show that some languages are not regular. Okay, so I hope that this helped you understand a bit more intuitively what we're talking about. Now let's see an example. How can we use that to say that 0n, 1n is not a regular language? Well, we're going to find, the first step is to find a S that is greater than a certain P, number P, okay? Well, the best way is to define S in function of P so that S by definition is greater than P. So let's take, and P is the pumping number. It's the number, it's because we talk about pumping because then once you have this number, you can pump as many times through the loop. It will stay in the language. But P is not a number you actually have to find. It's not like a concrete, I mean, it's an abstract number, right? But ultimately, you can think of P really as a total number of states in the machine. That works that way. So for 0n, 1n, well, let's take S, is 0 and 1n regular? Well, we're going to prove that it's not with reductio ad absurdum. Okay, so by assuming it is regular. So if it is regular, there is a S. So take S equals 0p, 1p. Okay, S is greater than P. The length of S is greater than P. That's obvious, right? There is P zeros and then P ones. Okay. Now, because of the lemma, we're saying that there is a way to divide S into X, Y, Z such that X, Y, Y, Z will also belong to the language. We'll have the form of 0 and 1n. And why X, Y, Y, Z? Because X, Y, Y, Z is, it's one of the possible instantiation of that if you take I equals 2, right? So X, Y, Y, Z is X, Y, 2, Z. But it actually should be true for any I, but here I'm just taking I equals 2, and it's going to be enough to show it's not regular. So how can I divide 0, 1, there's P for each of those. How can I divide S into 3 parts? Well, there are 3 ways of doing it. Either X falls in the middle of the zeros, okay? So either you so the Y, let's consider more the Y, the middle part, okay? Either the middle part here is going to be this one, or it's going to be somewhere like this, or it's going to be somewhere like this, right? You have 3 ways of selecting the Y, the looping part. Either it's a bunch of zeros, or it's a bunch of zeros and ones, or it's a bunch of ones, okay? Whatever you take, X, Y, Y, Z is not going to be in the language. Why? Because if you take option 1, okay, that's option 1, that's option 2, and that's option 3. If you take option 1 or option 3, what happens? Well, you have more zeros than ones, or you have more ones than zeros. And therefore, S doesn't belong to L because you don't have the same number of ones and zeros. If you take option 2, then you can have the same number of 0 and 1, but you're going to have necessarily a switching of zeros and ones, right? Because if you do x, y, y, z with 0, 1 in the middle, you're going to have 0, 0, 0, 0, and at some point you're going to have something like 0, 1, 0, 1, and then 1, da, 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 da. Okay, and it could be actually more than that, right? You could have 0, 0, 1, 1, 1, 1, 0, 0, 0, 1, 1, 1, 1. It doesn't matter. You have an alternation, I don't know how I say that in English, of zeros and ones, and that doesn't meet the requirement of 0 and 1n, which requires all the zeros first and then all the ones. So whatever you pick as y, S is going to end up to not be in L. So you cannot satisfy the third condition, the third criteria of the pumping lemma. So we just said, well, assume S is regular. Assume the language is regular. Therefore, the language is not regular. So we just proved by